Hello and welcome. Today we're going to put on our digital hard hats because you and I are becoming architects. We're going to build a fantastic study guide, a real blueprint for creating databases that are strong, reliable, and super efficient right from the ground up. Okay, so here's our plan for the day. First, we'll tackle that initial mess, moving from chaos to structure. Then, we'll open up the Architect's Toolkit to see our essential tools. After that, we'll spend some time refining our design, then actually bring our data to life, and finally, we'll post a guardian at the gate to keep everything safe and sound. Let's get to it.
Every great project starts by solving a really fundamental problem. And for us, that problem is messy, disorganized data. We're about to take that chaos and build it a proper home with a solid foundation.
So you've got two choices, really. On one side, there's the data shack, a flat file. Think of it like one giant spreadsheet. Sure, it's easy to get started, but man, it gets messy fast, full of errors and duplicated info. But on the other side, you have the skyscraper, a relational database. This is the smart way to build. It organizes everything into separate, connected tables for each thing, what we call an entity, like a customer or a product. This structure is organized, reliable, and it's built to grow. It's the only real choice, honestly. All right, so we've wisely chosen the skyscraper model. Now it's time to open up the toolkit. Let's take a look at the absolute must-have components that every digital architect needs to master to get this structure built right. First tool out of the box, the primary key. This one is absolutely crucial. It's a totally unique ID for every single row of data in a table. Just like your driver's license number is unique to you, a primary key ensures no two records are ever the same. It means we can always find exactly what we're looking for with zero confusion. Next up, we have the foreign key. And this is where the magic happens. This is literally the glue that connects our different skyscraper floors or tables together. We just take the primary key from one table, say a unique doctor ID, and we place it in our patient's table. And boom, we've just created a relationship. This right here is the relational in relational database. And then there's the secondary key. Now, think about this. Trying to find a specific page in a massive book without an index would take forever, right? A secondary key is exactly that. An index for our data. While the computer loves using the primary key, we humans often search for things like a last name. By making surname a secondary key, we make those kinds of searches lightning fast for the user.
So how do we actually draw up this blueprint? It's a pretty straightforward three-step process called entity relationship modeling. First, you just identify the main things you're storing data about, like your customers and your orders. Second, you list out their properties or attributes. And third, you use those primary and foreign keys we just talked about to connect them all up. Simple as that.
And those connections, those relationships, they can look a few different ways. Just like in the real world. You can have a simple one-to-one, like one husband to one wife. A very common one is one-to-many, like one mother can have several children. And then you get the more complex many-to-many scenarios, like many students signing up for many different courses. Okay, our first draft of the blueprint is done, but we're not ready to build just yet. Now it's time for the engineering review. This critical process is called normalization, and it's all about finding and fixing weaknesses in our design before they become big, expensive problems later. So you might be asking, why do we need this extra step? Why not just start coding? Well, normalization is our quality control. It's how we stress test our own blueprint to make sure we've created the most efficient, logical, and robust layout we possibly can. It's about preventing problems before they ever happen. Really, when we normalize, we're aiming for 4 big wins. First, we get rid of redundant data, which saves a ton of space. Second, it keeps our data consistent. So if a customer changes their address, you only have to update it in one spot. Third, it makes it super easy to add or remove records without messing anything up. And finally, it sets up our data perfectly so we can ask really complex questions and trust the answers we get back. All right, the blueprints are stamped and proved. Now we get to move from design to the actual construction. And the main set of power tools we're going to use to build, manage, and basically talk to our database is a language called SQL.
But hang on, before we can play with the data, how does it even get into our system? Well, in the real world, it happens all over the place. Think about how those multiple choice tests get graded by a machine using optical mark recognition, or how a bank instantly reads your account number off a check using magnetic ink character recognition.
Okay, so once that data is captured, it lives in a table that looks something like this. Let's use this simple movie table as our construction site. You can see each movie has a unique movie ID, that's our primary key, and then we have the title, company, release date, and director's name. Pretty straightforward. Now for the fun part.
we can talk to this table using SQL. Let's translate what this command is actually saying. It's like we're telling the database, hey, select the movie titles and their publication dates from your movie table, but I only want the ones where the date is between the start of 2000 and the end of 2005. Oh, and could you please order the results by date for me?
And boom, here's what it gives us back, instantly. It's not the whole table, just exactly what we asked for, a clean, filtered, and sorted list. That is the incredible power of SQL. It lets us find the exact needle we're looking for in a gigantic haystack of data.
And that's just scratching the surface. SQL lets us do way more powerful stuff. We can use a command like join to pull data from our movie table and our director table at the same time to get a bigger picture. Or, if we spot a typo, we can use update to fix it. With SQL, you have total control over your data.
So, our skyscraper is built. It's filled with valuable data. But our job as the architect isn't quite done. Now we have to become the building manager. We need to install the security systems and safety protocols to protect our creation.
One of the most important safety rules is something called referential integrity. All this means is that the database enforces rules to make sure the links between your tables never break. For example, it would stop you from deleting a director from your directors table if that director still has movies listed in the movies table. It just keeps things logical.
Now, to make sure every single operation in our database is rock solid, we follow a strict code of conduct called ACID. Think of it as the official building code for our data. A is for atomicity. An operation is all or nothing. C is for consistency. No transaction can ever break the database's rules. I is for isolation. Multiple operations happening at once won't trip over each other. And D is for durability. Once you save something, it's saved for good, even if the power goes out.
But what happens in a really busy system? Let's say you have two different people trying to access the exact same piece of information at the exact same time. This is a super common scenario, and it can cause some real problems.
Well, you can run into a nasty situation called a deadlock. Picture this. User 1 locks a record to make an update. At the exact same time, User 2 locks a different record. But now, User 1 needs the record User 2 has locked, and User 2 needs the one User 1 has locked. What happens? They're both completely stuck in a digital standoff, each waiting for the other to release their record. The system just freezes.
And that brings us right to our final question. Now that you're the architect, you understand the principles of design, construction, and security, how would you solve this deadlock problem? How would you design a system to stop it from happening in the first place or to cleverly fix it when it does? Answering questions like that, well, that's what turns a good architect into a truly great one.